We started derivatives by using the definition, which was the limit, cast it out there, reel it back in. Then once you proved that to me, then we did power rule, then we did product rule. And remember, product rule all on its own, not as helpful. Once we pair it with another one, it's hugely helpful. This one saves a ton of time, although it's not easy in itself. But if you take a look at the one we're going to take the derivative of down here, 3x squared plus 5 all over x squared, doing that by the definition would be horrendous. Remember when we did 1 over x by the definition, and it took forever, right? And so just imagine how much fun this one would be. And so, yeah, this one looks a little bit more complicated, but where do you suppose they came up with quotient for quotient rule? It's a division problem, exactly. And notice that we are taking some function, they called it here f of x, and we're dividing it by g of x. Again, if you want to write it in that other notation, you can say it's u over v. That's what some people do, again, because they like, it's a little bit simpler for them. Yes? You mean the square that's on the bottom? Or the question was, can we just subtract the square that's on the bottom? And unfortunately, we can't, because not all of the terms have a g of x in it. The second one, there's g prime of x. So that's not g of x. It is different. It'd be great if it was, but it's not. Okay, so if it is u over v, well, let's see if we can translate what this is saying. This one, though, there is division involved, and should be, by no surprise, subtraction involved, because those two kind of work together. Yesterday we had product rule, so it really didn't matter what order we did things, because it was multiplication and addition. Well, today it's hugely important, the order in which you do things. So I kind of look at it this way, and hopefully, again, you're getting better at reading this notation. It says, if I'm going to take the derivative of f of x over g of x, the first thing I should do is put g of x on top. So in other words, write down the bottom, correct? Or write down the denominator, times the derivative of the top, minus, and then do top, derivative of the bottom. So again, you see how you do both combinations, but now it's subtraction. So the order is hugely important, right? And then you divide it all by whatever g of x is, square it. So you basically take your old denominator and square it, okay? But remember what I said is normally don't multiply out until it's absolutely necessary, right, with denominators. And they have a little note over there that g of x cannot equal 0. How come? Yeah, you'd be dividing by 0, okay? And let's say if g of x was 0, this wouldn't even be a problem, right? But they do put that stipulation in there to show you that. And so if you want to switch it over, this would be what? V u prime minus u v prime over v squared. For those that want to write it that way, it does shorten things up a little bit, as long as you know where things go. But a lot of people like to say bottom derivative of the top minus top derivative of the bottom. And you can't really see my prime there because it's in the thing, but there you go. Well, let's give this one a shot then. So I got to take the derivative of the left side, so we're just going to write that as y prime. Okay, that's how you do that. Equals. Well, it says I got to write down the bottom. The denominator is x squared, so we'll write it down. And now I have to take it times the derivative of the numerator. And what is the derivative of this particular numerator? Yeah, I just pretend it was a separate problem, right? Just 3x squared plus 5. What's the derivative? It happens to be 6x. So do you see how these shortcuts are trying to let you use power rule as much as possible? Right? That's what they're trying to do, instead of having to go through that long definition. So minus. Now you have to write down the top, or the numerator, times the derivative of the bottom. Again, it's letting you use power rule, so 2x. All divided by x squared squared, or in this case, this isn't all that scary, right? So we could probably just write x to the fourth if we wanted to. This one isn't bad. But if you have like a binomial down there or something like that, don't worry about actually foiling it out, right? Just leave it like that. But this one's pretty easy, bx to the fourth. So now what we need to do is kind of just clean things up. Remember from Algebra 2 that this big long division bar is a grouping symbol, right? Do the numerator and denominator separately. Okay, it's the most commonly forgotten one, but it is. So this term here, I can work with that. That's 6x cubed, right? Minus, well now this is where you got to be careful. And so there's that minus again, right? So whenever you have that, I would probably do a bracket just to make sure I don't mess up, right? And so let's go ahead and distribute. We got 6x cubed plus 10x, right? All over, and like I said, this one's no big deal, so we can just write x to the fourth, right? Okay, I'm going to write equals over here because we're almost there at this point, but a lot of people do get going a little bit too fast and do this wrong at the end. They, oh, the 6x to the third minus 6x to the third, ooh, that cancels. And then they tell me that this is the answer. Yeah, very good. You got to distribute that negative all the way through. Excellent. And we can do one more little thing. This doesn't always happen, all right, but it happens here, that it is all multiplication in the top, correct? And we have pretty much all multiplication just written as x to the fourth in the bottom, right? And so we can actually go ahead and get rid of one of those, and it turns that into that, correct? So the derivative here, written in its nicest form, is negative 10 over x to the third. Now remember, that's a really nice generator. I can put any x value in there now, and it's going to spit out that slope at whatever x value I choose, as long as that x value is in the domain. And there's really only one x value that's not in the domain, and that's 0 in this case, right? Because 0 would make the denominator dividing by 0, and that's no good. Okay, so there's your derivative. Now I told you this is not as easy as product rule, right? But just imagine how far we would be if we were doing the definition right now. We would be nowhere near done. Okay, and the reason these shortcuts are nice is because they let you use power rule almost all the time. Okay, it's just following the pattern. And all of these shortcuts are possible because of all that canceling out that happens when you do the definition. So the only time you're really going to want to use this is if it is division, and this one is division, right? There is something in the denominator. And so, for example, if you want to just look up here real quick, let's say this wasn't here, I would not use quotient rule on that problem. I would actually just divide them all by 2 and use power rule. Could you use quotient rule on that problem that I have now if I scribble that out? You can still use quotient rule on this. But when you do the derivative of the bottom, you're going to get 0, and so half of that stuff goes away, right? So you can, but I would say use the easiest way. But the one that we have here, we actually do have to go ahead and use quotient rule. And so how's that start again? Quotient rule, you write the bottom, all right? So, and you just write it down. And then you have to take the derivative of the top. So 4x minus 4. Yeah, minus, yep. Very good. We're not quite to the all over part. So you got to write down, what, the top now? Is that kind of one way you could talk about it, right? And then times the derivative of the bottom, which is negative 3. Now all over the bottom squared. Now again, this is the case where I would strongly recommend don't worry about multiplying that out, okay, unless it becomes absolutely necessary at the end, but most times it does not. Now what some people want to say in this case is they look at this one here and they see that one there and they want to cancel them. But do you see that same term over here anywhere? You don't. And see, there's that subtraction, right? And so you have to have it in all of those locations, and we don't. It'd be great if we did, but unfortunately we don't. And so now we're going to kind of just clean things up. So yeah, unfortunately this one does turn into FOIL, but at least that's something that we can all do. So 8x minus 8 minus 12x squared plus 12x. Again, here's where I'd be hugely careful. Minus, might as well just take your time. No sense going through all this work and then getting it wrong. Or what you could really do is just distribute this negative to this term over here and make it a positive 3, but that's up to whatever you want to do. Because this distributes to one or the other. So this would be, let's go ahead, this is negative 6x squared plus 12x minus 9. And again, I don't see any reason that we would have to multiply this out at this time, so we'll just leave it. There's nothing that's showing up that makes me believe that's going to help me at all. So y prime. Well, what can we do here? Well, I'm going to go through and just do this. Change all these signs, right? Because then we don't need the bracket anymore. Save me a little bit of time. And so what do we got? We got some 12x squareds here, right? And we got 6 of them there. Anything else there? I don't see anything. So what, negative 6x squared? So then I got those, right? And I got an x here, x there, x there. Is that 32? Oh, there you go, plus 8x. Very good, because that one is subtraction over there. And plus 1. Now, is that my derivative? So that's the numerator of my derivative, right? There's my derivative. A little bit bigger generator than we've had before, but it is still the generator given any x value. I would leave it. Now the question there was, do we have to deal with that denominator? I don't see any reason that we would need to multiply that out, because it's definitely not going to become the numerator by looking at it quickly, right? There's no way it's going to be that, so it's not going to cancel or anything. So I don't think it makes more x's in the problem, really, if you think about it. So that kind of goes with what I've been saying. Once you get to calculus denominators, don't have to worry about them so much anymore. Okay. Now the question is if I knew the x value, could I have substituted the x value in this green spot if I knew the x value that I was interested in? I could have, right? But that's a lot of places to substitute it in, right? But if you know it, you could have done it there. The reason we do this is, what if I have a lot of x values that I want to put in? And another reason we do this is, what if I'm looking for a particular slope? Then I would set it equal to that number, right? And then we'd have to do the algebra. Way easier to do algebra with what's written in black right here than what's written in that green and trying to do it from there, right? And so that's why we do simplify them. That is quotient rule. Okay, any questions on that? Okay. Again, it's a way of letting us use power rule as much as possible. And as we did with product rule, we are going to look at things like this. So again, we have two functions, u and v, that are differentiable at x equals 1. Do I know if u and v are differentiable anywhere else? Nope. But I know they're differentiable at x equals 1. And I got a bunch of information here about various numbers here. So let's see what we can do. Determine the following derivatives at x equals 1. Okay. Well, here's u over v, right? So we have to take the derivative. Have we seen function u or v? No? But more than likely they got some x in them or something like that, right? But we haven't really seen them. So I don't know what actually are in those functions. But I do know if I try and divide them, two functions divided, I can use quotient rule, right? Which is v, u prime, minus u, v prime, over v squared, right? Now, which x value am I most concerned about? I'm concerned about 1. If I have to find, for this right here, I have to find v of 1. For that, I have to find u prime of 1, u of 1, v prime of 1, and v of 1, and then square it. Agreed? So what is, let's just go in order, what is v of 1? Where do we find that? V of 1 is right here, right? Is 2. Agreement with that? Times u prime of 1 is negative 2 minus, what's u of 1? 4, right there, times v prime of 1 is 4. Right, did we see that one? All over v of 1 squared. Where's v of 1 again? V of 1 is 2. So 2 squared. So what do we got here? Negative 4 minus 16 over 4. Negative 20 over 4. Negative 5. What does negative 5 represent? The slope of the tangent line at an x value of 1 for what? For u? For v? For what? Which function is that slope of at x equals 1? U over v. Yeah. It's the slope for that function. We haven't seen u, we haven't seen v at all. We have very limited information about any of it. Yet, if there was a function u divided by v somewhere, we now know that the slope is negative 5 given the values that we were given. So what's all this stuff about? Yeah, I wanted to see if you'd use it. Does it help us with this problem? No. Because for one, I don't know it's differentiable at either one of those places on those. And so, well, I'd actually know here because it got a slope. But okay. Questions on that one? Is this the same problem? Is it the exact same problem? No. So I would like you to try letter B right now on your own. If you're listening to the recording, please stop it and actually try it instead of waiting for me to just play it again. All right. Very similar problem, but the key, and the reason I'm doing these is actually for when we get to a little bit harder rule, which I think is probably coming next, that you can write it out in symbolic form, because a lot of people can't. They can do it, but they can't write it out in symbolic form. If you change anything, all of a sudden they can't do it. Well, if this is what it is, it's bottom, right? Derivative of the top minus top, derivative of the bottom, all over the bottom squared. Agreed? And we're looking at 1 again. We know it's differentiable there, so we're good. And so u of 1 would come first, which is 4. And v prime of 1 is 4. Those of you that were clever probably realized you just had to work with the stuff you had previously, right, on the other problem. V of 1 is 2. And u prime of 1 is negative 2. All over u of 1, which is 4. Squared. So what do we got here? 16 plus 4. Those numbers look really familiar. Over 16. 20 over 16 is 5 over 4. Again, 5/4 is the slope at x equaling 1 of that function. A function we've never seen. And this one. Very straightforward. Again, u is some function that probably has x's in it. So do we know what the derivative is? No, we don't know what the derivative is. But I do know the best way I can notate it is u prime. It's the best I can do right now because it's with respect to x. So there's probably some x in there. I just don't know how to write it right now. But if somebody were to give me that function, I could do it right away. And then plus v prime. And so now again, it's at x equals 1. We know it's differentiable. So all I need is u prime of 1, which is negative 2, right? And plus v prime of 1, which is 4. And so we get 2. Again, 2 is the slope at x equals 1 of this function. Again, it's very possible that if I gave you two functions, you could actually add them together and combine like terms and all of that stuff, right? Maybe you can't. I don't know. We don't know what those functions look like. And so we have to give it in the best form that we can. Again, it's with respect to x, and there's probably x's in there somewhere, but I don't know. I don't know what it is. But I do know this information. Okay? And so we should be able to get to the answers. Okay? If you have any questions about quotient rule,